Let's consider now polyprotic acids. These are acids that can donate more than one proton. So as a general equation, we can have the diprotic acid where we have two hydrogens that the acid can donate, and it will react in water. And the first proton can be donated to water. And its conjugate base is formed, and then this other species has a single proton left to donate, and so it can also react in water to donate its proton. Giving the conjugate base A2-. So this is an example of a polyprotic acid where we can donate two protons to water, and so we have two reactions that can be in equilibrium with each other. So we can form a Ka for the first reaction and a Ka for the second reaction. So if we write these, this is the Ka for the first reaction, we call it Ka1, and Ka for the second reaction, is this for the second reaction, so we call it Ka2. And usually Ka2, the subsequent reactions, are much less than the first reaction. So as a general rule, Ka2 would be much less than Ka1. So in this case, let's see what happens using the Chatelier's principle from equilibrium. So we formed H3O plus in the first reaction. And if Ka1 is much bigger than Ka2, then Ka2 reaction lies heavily on the reactants. It just forms a teeny bit of products. Well, since we've already formed H3O plus from the first reaction, this is a product in the second reaction, and so the fact that we're forming H3O plus from the first reaction being a product in the second reaction drives the second reaction back toward the reactants because we have too much product now for this second equilibrium. So it inhibits the second reaction even further. And so even though this has an equilibrium, the fact that we're forming H3O plus in the first step inhibits the production of H3O plus in the second step. So this reaction can become negligible. So usually for polyprotic acids, we just consider the first reaction because the second or third reaction has become negligible due to the fact that a product, H3O plus in this case, is formed in the first reaction and suppresses subsequent reactions. So let's do an example that illustrates this. We'll look at the polyprotic acid, sulfuric acid, and it has two protons that can be donated. So this is the first step. Now you notice the first step goes to completion. I haven't written a back arrow. This is not an equilibrium. H2SO4 for the first step is a strong acid, so it goes all the way to completion. Then the second step, HSO4 minus, so this proton can also be donated to water. Now this is an equilibrium because this is a weak acid. And so since the first step is not an equilibrium, it goes 100%, it doesn't have an equilibrium constant. So only the second step has an equilibrium constant. And I'll write that. So this is Ka for the second step, 2. And this is equilibrium constant, and this is still fairly large, 0.012. So now let's look at the consequence that this H3O plus formed from the first step will have upon the equilibrium of the second step. So this is a strong acid. It completely reacts in the first step to form H3O plus. Then that H3O plus, being a product of the second step, is going to affect this equilibrium. And so from Le Chatelier's principle, if we overload product, we'll have to drive the reaction back toward reactants to reestablish equilibrium. So that means that even less of the HSO4 minus is going to react than would have if we didn't already have H3O plus present from the first step. So let's look at this numerically. So say we have HSO4 minus reaction and we have our equilibrium constant. And it's equal to 0.012. Well, let's pretend for a minute that there's no H3O plus coming from the first reaction. Let's just pretend that this is by itself. So we're just going to see how much H3O plus would be formed if this reaction was the only one in solution, and then compare it to what actually happens. So in this case, we can use our equilibrium tools, and so we can just let X be the amount of H3O plus formed from the second reaction and plug it into the equilibrium expression. And let's say we start with 1 molar, so I is 1.0 molar. So then we'd have X squared over 1 minus X. And solving for X will give me 0.10. So that means that the H3O plus concentration is 0.10 molar just from this step. So just from this second step, the H3O plus concentration wants to be 0.1 molar if the initial concentration of HSO4 minus is 1 molar. But now let's look at what happens when the first step actually is present in solution. So the initial is 1.0 molar. So we're going to have okay, so we'll have this table. So this is the amount of H3O plus coming from the second step of the H2SO4 reaction, and this is the initial concentration of HSO4. And remember, we have these two reactions. There's no equilibrium for the first step. Okay, if H2SO4 is initially 1 molar, then we're going to form 1 molar HSO4 because this top reaction goes completely to products. So if we start with 1 molar HSO4, we're going to produce 1 molar HSO4 minus because this reaction has gone completely to products. No more H2SO4 left. So that's how much HSO4 minus we're starting with. Now, if we neglect the H2SO4 reaction, we saw that the H3O plus concentration wants to be 0.1 from the second step. But if we allow the first step to exist, as it actually does, then let's look at what happens. So if the concentration is 1.0 molar H2SO4, and we actually let the first step to exist in the equilibrium, then the amount of H3O plus from the second step has been reduced to 0.011. So now you see that allowing the first step to exist in solution has suppressed the amount of H3O plus that's produced from the second step. So without the first step, it's 0.1 molar H3O plus produced. But if we include the first step, this H3O plus is suppressing the second reaction. So now we only have 1/10 of the H3O plus formed from the second reaction. So the first reaction has suppressed the second reaction.